Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Now it's day 12, so the last day of this lecture series on high entropy alloys and some of their associated properties, specifically microstructure-diffusion correlations. We have now been looking at specifically some grain boundary and volume self-diffusion measurements on some of the high entropy systems. Mostly it was on the Cantor alloy, so FCC system, because this was the system and still is the system that has been mostly studied because it's the most simple one, also one of the first that have been discovered. Now let's go a little bit away from FCC materials, especially as I told you, this is because first of all, not much work has been done, so none of what I'm telling you today will be found in any textbook yet. And also some of these materials and alloys, which I'm going to talk about today, will have more, at least from my perspective, potential to go earlier into any type of application. When we now think of these RHEI, the refractory high entropy alloys, then this alloy, the titanium, zirconium, hafnium, niobium, tantalum, is really the most researched one so far. It has very high strength up to very high temperature, and at the same time good ductility at room temperature. So it can be machined, it can be processed at room temperature, which is very important for any application, but it has a very high strength up to high temperature. So it's really something like very model-like material for high temperature applications. And as far as we know, it is also available as a single phase high entropy system. So it means one common lattice structure and elements are distributed over the lattice sites at random. Obviously, whenever you treat the material so that either kinetics are enhanced at some temperature, or if you wait long enough at lower temperatures, the material will be showing tendencies for destabilization of the single phase solid solution, and we have discussed why this is. So in this case, if temperature treatment is done at temperatures less than 1000 degrees centigrade, so quite at a high temperature already, then the chances are very high that for the compositions one typically chooses, second phases precipitate and form. One bad property of this material is that it is not very strong and resistant against environmental degradation, so corrosion. And here it's called pest oxidation. Do you know the term? It's basically like when you have poisoning by any element like sulfur or phosphorus or gallium that goes along the boundaries and basically causes the material to disintegrate literally, so basically falling apart into their grains. And this can happen here by the oxygen going along the boundaries in a very fast way, forming an oxide, and that then is very brittle, and it can then basically under very small mechanical forces fall apart. And this is probably related also to stress, corrosion, cracking, right? So you basically build up an oxide that has a different specific volume, so it expands, and that opens a crack, and it opens, unfortunately, a crack along the grain boundary. Oxide can move along the crack, oxygen very fast, form new oxides, and so it's a self-accelerating process leading to complete and catastrophic failure. So that's bad. And I will also talk about the so-called sigma phase in, again, the Cantor alloy. This is a chromium-rich phase, which forms at lower temperatures in the FCC model alloy Cantor system, cobalt, chromium, iron, manganese, nickel. And it is also normally, because it's known also to form in steels, a phase which you do not like to have. Because again, it's brittle, and that means sigma phase leads to embrittlement. So it's something which you normally would like to avoid in your microstructure. However, in this case, it's nice because at the very fine scale, the sigma phase can really provide a hardening phase, while the majority is still FCC, so you can get precipitation hardening very efficiently from that phase. And in this case, it's also can be thought of as a high entropy intermetallic, because it consists of also the ingredients as of the Cantor alloy. And so we will also talk about how the diffusion in this intermetallic compound phase, when it's having many different constituents, will take place. So if we now go to the first part, diffusion in the titanium, zirconium, hafnium, niobium, tantalum, we compare it to a variant where we replace the tantalum with vanadium. Now when you think about what we have talked already about and what do you know about tantalum and vanadium, what would you think is the major difference, or why do we pick vanadium to replace tantalum? What is the largest difference between these two elements?
Affinity to form precipitate. Steel, we replace, like to avoid chromium carbide formation, we had vanadium.
Yes.
Similar thing maybe.
Exactly. And it's because, again, also of the smaller atomic size of the vanadium, so it fits much nicer into the remaining constituent elements, while tantalum is a very large atom, right? So it creates a lot of locally atomic level stresses, and that can accelerate also phase formation. And it was the idea here to basically replace this then by a smaller one, see what this does.
So that will give toughness also.
That will give also toughness, yes. Yeah. But tantalum itself is also a toughening ingredient, often in many alloys, because tantalum is a weird element in the point of view where it is situated in the periodic table. I don't have a good explanation for it, but when you look at it, actually also for materials that undergo diffusively driven amorphization reactions, also tantalum often is a key ingredient. I think it might be related to this very complex electron structure that tantalum has. It has so many electrons, and they might form some like hybridization orbitals, or maybe not really fully developed, but have a certain different electronic configuration around them as compared to titanium or zirconium or so. But that's just, you know, a hypothesis. I cannot prove it. So you see here, as a function of normal distance, these penetration profiles, and you see them for the two alloys marked by either crosses or these squares. And you typically see that here for the crosses, so for the tantalum-containing alloy, you have here the nice demarcation between volume and grain boundary diffusion. For the vanadium containing system, that is not so obvious here, right? What would you think of the profile shape here? It is mostly grain boundary, exactly, yes. Could you think of a reason why it's so different between the tantalum containing and the vanadium containing material?
You said that is smaller size for precipitate, so that it mostly preferred at grain boundary, so that's why.
Yeah, I think it is related maybe also to the homologous temperature again and the relative importance of volume and grain boundary contributions. They are always both there, right? But
both are like near par. They are both like tantalum and vanadium. I think both are nearly equal.
yeah, the two alloys have a little bit different melting temperature. Yes, yeah. So you cannot always judge between the melting temperatures of the constituents. You always have to look at the alloys themselves, right? Yeah. This is instantaneous source solution, and this is then the Harrison B-type classification. Obviously, because you see very pronounced, you have grain boundary and volume contributions, and then this needs to be applied. We then analyzed the zirconium diffusion. So zirconium was the tracer. And you can see here a comparison again of tracer diffusion, radio tracer diffusion of zirconium in the pure elements titanium and zirconium. This is the black solid line as well as the dashed line as compared to data for the two alloys as just indicated. And this is basically then the geometric mean, the green curve here. So this would mean this is the value you would expect if you calculate just the geometric mean for zirconium diffusion in these refractory high entropy systems based on the diffusivity of zirconium in each pure constituent. And then basically you again see this as a comparison on the homologous scale as well as on the absolute temperature scale. What is your opinion? Diffusion is sluggish, or is it not sluggish? I think the good comparison is really given by this geometric mean. And this is basically showing it's not sluggish. It is actually a little bit faster as compared to what you expect as a reasonable comparison from the pure constituents. I would also not go as far as telling this anti-sluggish behavior, because it's just within the variational span we would expect going from pure constituent to a 5-component alloy. But certainly it is faster as you would expect if you do a simple calculation of what you would expect for the 5-component system, right? So it means again an example that diffusion is rather going along as normal. You cannot predict from any textbook knowledge how the specific diffusivity of a complex alloy would be. So you have to either do atomistic calculations or you have to do real measurements. You will not be able within 1 or 2 orders of magnitude to predict really the diffusivity of a given alloy. Our knowledge is just not advanced enough to give that kind of knowledge. yeah, so a little bit enhanced diffusion, but I wouldn't say it is much. And here it's just again compared zirconium diffusion coefficients in the two refractory high entropy alloys to various other BCC matrices. And then again for the absolute temperature and for the homologous temperature. And again, not much of a difference. Something we have not yet described or discussed is potential energy fluctuations. People discuss this for the high entropy systems, and it's related to these lattice distortions in a way, right? So you basically have more distortion, so you have a certain additional energy term because of these strains. So it's an elastic energy density which is added, and that gives you for certain sites an enhanced energy, and it will vary from lattice site to lattice site to lattice site, and this is then called potential energy fluctuations. So the potential energy landscape, as we have discussed earlier, is creating highly unstable sites because maybe just out of randomness, some strains locally are very high, so positions in the energy landscape will be elevated along, so it's an unstable site. So basically if we draw an energy landscape, and again we have all the configurations in the alloys compared with respect to their potential energy, then we might have something very complicated, right? So it's not as in a typical relaxed alloy or a single element where you basically have a flat line almost. Here we would have some sites which are highly unstable because they are very high in the energy landscape. In terms of the diffusive jump, would you think this has any impact? It should.
There's
This,
too much energy required to like give that because they present bond.
yes.
Another with another atom. So if that that means that if the energy is high, so that means that much energy required to break that bond.
It's the other way around. This guy here will stay longer because it has more bonding strength, because the potential energy is lower. It feels well where it sits. And this guy here will jump faster because it's in such an unfavorable position, so any small additional, kick by energy just coming from the environment will put it into the next position. And so this is affecting diffusion. Slow diffusion, sluggish diffusion would be these guys.
Psi is an atomic constituent or radius or something.
Yeah, this is just a general thing for the average atom.
We plot E potential with
Yeah. We put just configurations and we put like an average atom there. Normally, as you rightly said, you would have a multi-dimensional representation here, because for each atomic species it would look different, right? Yeah. So when we now calculate based on the atomic size misfit, and we have already introduced how to do that, these are the given equations, and from there also calculate the chemical bond misfit, which is indicated here with these average bulk modulus, average atomic volume, and the mixing enthalpy between the different species. Then we would get to this sequence of diffusion coefficients in this alloy, right? So the diffusivities in these rather not high entropy systems would be larger as compared to the high entropy system at this temperature. But what also has been discussed in the literature is that sluggish diffusion is more likely to occur in a rather small window of given lattice mismatch between 1 and 3%. And if the lattice mismatch is larger, then it seems that faster, even accelerated diffusion can happen. And I think it's related to this potential energy landscape picture. When you have the larger lattice mismatch, then you have many of these sites which are energetically very unfavorable, and that can give rise overall in measuring accelerated diffusivity. And when we look at the lattice mismatch of these two alloys, they are both larger than 3%, so that might explain why here this high entropy approach has been overdone. So it's basically meaning you have added alloy constituents which do not really like to form a single phase solid solution. They still do, but they are on the brink of not doing. This is why they are also rather unstable against precipitate formation. And this means that here any type of entropic effect hindering diffusion is not present because it's overwhelmed by this potential energy fluctuations which give rise to accelerated diffusion in this very strong lattice mismatch condition. When we now look at an impurity tracer diffusion, so cobalt is not part of the alloy. So when we measure tracer diffusion of cobalt in these alloys, it is an impurity diffusion, right? So we have to take into account that there is a different contribution from the diffusion entropy relating the mixing of a new element with the given constituents of the base alloy. And when we now look at this impurity diffusion coefficient and compare it to the self-diffusion coefficients, this is then here, the zirconium, so self-diffusion. And these other two are the impurity diffusion coefficients in these two alloys. And we see that the impurity diffusion coefficients are much higher. Again, rather unexpected, because normally self-diffusion is more fast when you stay in the same diffusion mechanism. So here we expect it's probably still, or we could expect that it's substitutional diffusion, and then normally the self-diffusion is faster because the atom basically finds the perfect match when it goes to the new lattice site, which is not the case for an impurity material. When we do this again for the two temperature scales, the comparison, homologous and absolute, look at the impurity diffusion coefficient of cobalt in these two refractory high entropy alloys and compare it again to cobalt diffusion coefficients in other BCC matrices, and compare it also again to the geometric mean of the diffusion coefficients, then again it looks like we have enhanced diffusion on one temperature scale, retarded diffusion on the other one, but it's not a big effect. And again, looking for comparison between two refractory high entropy metals and BCC phases of these subsystems of the high entropy system, we have kind of the same acceleration, deceleration type, because going from absolute temperature to homologous temperature just changes for these systems a lot. So it means, again, we are here in the same situation almost, but a little bit more strongly concerning the numerical values which we see as compared to the Cantor high entropy system. depending roughly on how we set up the comparison, we can see that there is either a deceleration or an acceleration of diffusivity. In the end, it's within 1 to 2 orders of magnitude, and this comparison involves either a pure element high entropy system or high entropy system and some geometric mean coming from the pure systems, and that is certainly bound to a variation of a few orders of magnitude. Now, diffusion in the sigma phase. The sigma phase is displayed here, and you can see it's quite complex phase. So it is astonishing, I think, that you can have 5 elements finding their sites. It's certainly a completely different way a high entropy material is designed, because here you have certain sites which are assigned by nature for some of the elements, and other sites which are then assigned for again, the rest of the elements. So you see there are 5 inequivalent lattice sites. There's 30 atoms in 1 unit cell, and compositions traditionally range from AB7 to A7B. Normally it's a binary phase that forms. This is mostly studied in superalloys and in austenitic steels, and again studied because people like to avoid it. Right. Here we just take it as a model system for a high entropy intermetallic phase, and here diffusion was determined by time of flight secondary ion mass spectroscopy. This is then showing you how such a measurement would look like. So in real space we have a finely polished surface. We apply non-radioactive tracer, so like some isotope which is stable, but which is not as abundant in the natural isotope mixture as we apply it here. So normally we apply 100% enriched stable tracer, and in the alloy it might be that this isotope has a fraction of, I don't know, 10%, 5%, 15%. If it has more, then it's difficult to measure, because then your scatter will be larger, because your alloy will always contain some fraction of the stable isotope mixtures of all the isotopes. If this fraction is higher, then your applied isotope will diffuse in, but it will very quickly then reach the level of the base material. Then you cannot measure diffusion anymore. So you want to use a stable isotope for these measurements, where in the natural material its abundance is as small as possible. So you have a large contrast between the applied isotope diffusing into your material and the base level given in your normal material. Yeah, and then basically you sputter a crater, right? And then you do it continuously, so the crater gets deeper and deeper and deeper, and you collect information about how many of this specific isotope is present at each specific depth. Normally you would measure just as a function of time, and then you have to recalibrate your measurement afterwards by measuring the sputter crater depth at the maximum time. And then you assume that time and crater depth vary linearly with each other, so you have linear dependence on each other. Then when you do this, you get again a diffusion profile. So as a function of the depth into the sample, you get an intensity signal for every isotope present in your material, and then you just select the isotopes which you are looking at, specifically those you have applied on the surface. And you can also map this maybe with 2 isotopes, so we can later on map the ratio also, which basically gives you then a correlation which you can use in order to distinguish between different artifacts that could happen. Because the sputtering process in time of flight secondary ion mass spectroscopy also serves to mix the atoms, right? So you have some corrections which you need to do. Otherwise, the profiles work and are evaluated in a rather similar way. As
The position of detector here also.
yeah, it's more like you have
I mean, like which side of sample the detectors are there, or 4 detectors are there? How many? That are
normally you just have one detector. You have your sample. You have the sputtering beam, and you have your analysis beam, and you have here your extractor, which goes to the mass spectrometer, which is time of flight mass spectrometer, right? So with this sputtering beam, you dig into the depth of your sample. And with this analysis beam, you kind of nicely slice off just the top surface in your sputter crater, and these then go into your analysis column. So you separate out the digging from the analysis, because the digging will create much more energy input in your material. So you basically sputter off, but you don't collect that information. And then you stop, and then you just sputter off gently. This goes into the analysis column, give you the intensity profile, and then you stop again. You can dig deeper, and so on. So that especially is important for digging into the first original surface, because you will always have dirt there. You will have oxides, you will have nitrites, you will have some hydrocarbons which are adsorbed to the surface. You don't want to have this going into the mass spectrometer. And this is why you first clean off the surface, dig a little bit into the material, and only then you start the analysis. But then you only have one detector. This is this mass spectrometer, right, which is then time of flight. And that gives you a direct readout on the flight. Yeah, you just use the normal fitting procedures, and then you can, again, do this after you have annealed the material at different times or at different temperatures, giving you diffusion profiles. And here the nickel and the iron diffusion in the sigma phase is shown, again, for both ways to plot it. And for comparison, the diffusion rates of vanadium in the iron-vanadium sigma phase and the alpha phase, and iron in the iron-vanadium sigma phase are shown. You see, depending on how you plot, a little bit of a difference between the measurements in the high entropy system and the measurements in chemically much simpler systems. But again, I mean, here the difference is a little bit larger, right? So you could say here that you have an indication of some sluggishness of the diffusion process. So when we look at now lattice distortions versus chemical disorder in different lattices, we have FCC, BCC, HCP now for a comparison. We can see nickel in pure nickel, nickel in the high entropy Cantor, and nickel in a binary system. There might be some sluggishness, but it's not much. But also, when we look, for example, here in the HCP system or in the BCC system, we let a little bit larger variations. So when we look here, for example, at the cobalt diffusivities, either in the pure iron phases in a binary iron-cobalt alloy, or in this BCC variant of the former Cantor alloy, so you basically modify it by mostly aluminum, then you get a BCC phase, and then you basically see that you have here this comparison, so this value as compared to what is mostly going here. So this is certainly a deceleration of diffusion. If you go for the HCP comparison, you see that there is actually a comparison the other way around. So you have, for FCC, I would say, almost similar diffusion. For HCP, accelerated. For BCC, decelerated diffusion. The largest actually effect is for BCC, I would say, but in general we can say there is no pattern, right? So it could go.
It is like because same structure cobalt also is BCC.
Right.
That is BCC easily diffusing.
Yeah, but here it's rather sluggish, right?
The temperature is also there, like homologous, we see temperature. Like in FCC, it's diffusion at very higher temperature. BCC.
Yeah, I mean, yeah, there are slight difference, but you see there is a strong overlap here, right? I mean, this is the overlap between FCC and BCC temperatures on the homologous scale. So it's not so very big difference, and you see the Arrhenius plots are straight, they go continuously, you don't see a kink or anything like that. So it means the mechanism is probably unchanged for each crystal system over this range of temperatures. If there would be a change inflicted by temperature, we would see that at least there is a kink, a different slope in Arrhenius representation, even a jump could happen. It's not the case here, so I would say there is no real indication of any disruptive change based on lattice changes or anything like that. Why it is different in FCC, BCC, HCP is something which is very difficult to discuss because, again, also the chemistry are different, right? Because otherwise, if the chemistry is no different, how do you change the lattice structure, right? Yeah. If you look at it in terms of lattice distortions, certainly for the FCC, these are smallest. This is maybe why the diffusion is rather unaffected by going from rather pure to very concentrated solutions. BCC, HCP both have something like more than 3%, but maybe this limit of 3%, which was suggested in literature, is not wrong. Maybe it's more like between, but 3.8 and 4.2 is not such a big difference, right? And one goes down and one goes up. So again, there's a little doubt whether this can be put on a very general statement that a certain limited number of lattice distortion would give you either a deceleration or an acceleration of the diffusivity. I kind of a little bit doubt it. So refractory BCC high entropy alloys are high entropy alloys in the true sense, so they can form complete solid solutions. Also, this is true for the sigma phase. Sluggish diffusion was found not really to exist in all the high entropy alloys studied so far. And it seems that atomic size misfits and again the type of alloying elements plays a more pronounced role than having a complex composition. However, again, there is not yet an established pattern, so we cannot say a priori we take these elements and we have this type of lattice mismatch, this type of mixing enthalpies or so, and we would expect this type of diffusion behavior. Now, there is one incidence where we really have anti-sluggish diffusion in higher entropy systems. And this is when we look at diffusion in the multi-component pseudo-binary B2 aluminides. So we look at these aluminum nickel, aluminum cobalt, aluminum iron. They reveal long-range order even at high temperatures, so they are very stable as ordered alloys. And as you probably know, strong ordering tendency in an alloy makes diffusion to be decelerated. Why is this? Well, because if you have a lattice like this, so let's say this would be an ordered alloy, just a simplified version, the diffusive jump needs to go between here and here and here and here, right? It cannot really go from here to here, because this would destroy the local ordering. So it means this ordering is kind of a selection rule for which diffusive jumps could occur, and this makes it diffusion slower. And if we now apply this design concept to these aluminides, we need to think of sublattice alloying. So we need to introduce different elements and not just one on each sublattice to get pseudo-binary multi-component aluminides. And so we did this for this series of alloys where we basically have aluminum 50 as the base component, for one sublattice. And we have then on the second sublattice anything from binary to quaternary to ternary and also to 5-component systems. So we replace cobalt and nickel by cobalt iron, iron nickel, then we have all the binaries, then we go for cobalt iron nickel ternary, then we add manganese, and in the end add also copper. We want to check how this configurational entropy increase of a specific sublattice. So with two sublattices, we're only changing one. The aluminum sublattice is staying constant, and the other sublattice is then going from a binary to a high entropy system. Again, we have or can achieve uniform compositions about equiaxed grains, large grain size. We have in the material mostly high angle grain boundaries, and as you look from the X-ray, single phase ordered BCC. When we look at the volume self-diffusion, then we first look at the penetration profiles. We again see there are different contributions. And when you look now at this here, how would you interpret the three regions? Region 3, grain boundary, right? Would be my guess first when I look at the profile. Then region 2 probably means volume diffusion. There is a region 1, surface artifacts induced by the slicing or grinding in or so, absolutely, yeah. So one always needs to worry that there is something like this. So you basically make sure by some tests and evaluate only regions 2 and 3. Right? There's one thing which also looks a little bit strange, which is the very flat penetration profile towards long distances into the sample. So it's almost no slope, which means that the slope in this region here, in this region, the slope is very small, and that means the diffusion here happened really fast, right? Because the concentration is for long distance, I mean more than 20 micrometers or so, it's almost not dependent on the penetration depth. And that is basically indicating that the diffusivity is quite large. then obviously one can do these measurements for all the different systems, the binary, ternary, quaternary, and quinternary sublattice, and this is the result shown here. Diffusion coefficients of nickel and zinc in nickel-containing alloys as a function of the atomic percentage of nickel. And the tendencies are similar for cobalt and iron in cobalt and iron-containing alloys. And you basically see that when you look at the tendency as going from rather pure to rather high entropy sublattice alloying, that the diffusion coefficient goes up. And it goes up strongly. So we are here at a level of about 10 to the minus 16, and we are here at a level of 10 to the minus 13. So this is acceleration by roughly 3 orders of magnitude, going the wrong way, going from rather pure sublattice to high entropy sublattice. And that's very interesting, because we see that sublattice high entropy alloy design makes diffusion significantly faster. 3 orders of magnitude difference is much more than almost any high entropy effect in the other alloys has caused in terms of deceleration of diffusion. So the anti-sluggish diffusion effect in these aluminides is stronger than the sluggish diffusion effect in all the other high entropy systems we have studied. And it again shows there is a variety of different behavior which we find for the different high entropy systems, going again from slight deceleration, in one case a little bit more deceleration, but also going to acceleration, just depending on which specific high entropy system you are looking at. In all cases, it's like the same configurational entropy contribution which is taken into account. And that, I think, shows very nicely that there is no high entropy, or at least, no high entropy related tendency of how diffusivity would develop in a specific alloy system. So when we now look at the diffusion coefficients of nickel normalized to the melting temperatures of the compounds, it's a function of the combined nickel and cobalt concentration, then we again see the dotted line corresponds a general trend that we again see that an entropic term can both retard and enhance diffusion, right? So you see that and there is acceleration. So the entropic effect can go both ways, which means, again, and this is, I think, the common ground of all the last lectures and this one, there is no pattern. So we cannot say configurational entropy of mixing has this and that impact on the diffusion. It is much more subtle, and it much more depends on the specific interactions on the specific lattice site with the specific constituents we are choosing. So this is the unfortunate bottom line of the diffusion measurements. It's not easy and simple. We cannot have a common rule and that fits all. We have to really be very specific in terms of how we look at it. So tracer diffusion coefficients of the transition metal elements in the pseudo-binary B2 aluminides are again in the range that are expected. In the 5-component system, it exceeds the diffusivity, and this means hypothesis of sluggish diffusion has received another strong blow, because here we have anti-sluggish diffusion confirmed. Now, in the last few minutes, I would like to go for something which is very new and which you will not find in the literature. We will talk about interface diffusion, which means now we answer the question, how fast is diffusion happening at an internal interface, but on one side of the interface there is one phase, and on the other side of the interface there is another phase. You think this happens very much in nature and in industry and in any products, and you are right, but we don't know anything about the structure of these interfaces and the diffusivity, although it's so important for interconnects. Just the information is not there. This is one of the first studies where this has been investigated. We took a high entropy system for this case because of specific requirements on all the techniques which we need to use. TEM, diffusion measurements, SEM, all the others, and the material should not form oxide very quickly so that it prevents high resolution electron microscopy. It should have good tracers available and so on. And so all these selection criteria, which are only technical, made us go for this high entropy system. What we took is dual phase high entropy, so it means like a eutectic high entropy system, right? And you can see here that we have eutectic between an FCC and a B2 system. Obviously, this would also be nice and good if you think of the mechanical properties, because you basically have a ductile and a hard phase again. And it's only this two-phase solid solution which we have. And we have single-phase sharp melting because we have a eutectic alloy, right? So this means all the phases which take place are participating and melting together. This is how it looks like. Very nice eutectic microstructure in the SEM. And basically, you can see the orientation distribution of both phases, FCC and the BCC, the B2 phase. So only two phases present. Concerning chemical distribution, this is also nice because we can see that we have rather uniform chemistry. And now we have to look a little bit careful because we have now two interface types. We have grain boundaries, or we have three interface types. We have grain boundaries in the FCC phase. We have grain boundaries in the BCC B2 phase. And we have interfaces between FCC and B2. Now, when you think of, you want to analyze the diffusion along internal interfaces in such a material, you need to worry about several different things. You need to worry about how much interface length per unit area is there for each of the type of interfaces. And you need to also worry about how is the interconnectivity, the percolation of each type of interfaces. Because if we do not have a percolating, a fully interconnected pathway, then this does not contribute to really long-scale diffusion. And so it means we have now to analyze the microstructure in terms of also how much interface area is there and how much of this interface, these interfaces is interconnected. Nice thing is we see that there is no pronounced segregation of any element at these grain boundaries as well as the phase boundaries. So that means for the later analysis, we can basically think of the factor S, the segregation factor, to be unity, and that will be simplifying things a lot. This is now going to TM investigations of the same material, and you can see here, you get these No, I didn't want to do that. I wanted to change here. You see there are interface boundaries between B2 and FCC, grain boundary, and FCC1, FCC2 means just two different grains, and here is again an interface boundary. When we look at these electron diffraction pattern, which you see here, so selected area electron diffraction, you can see nicely B2 and FCC patterns. Not always nicely resolved because some of the misorientation with respect to the direction of the incident electron beam are such that you do not see all the reflections. When you analyze them, then you see that we have preferentially an orientation relationship known as Kotyumov-Sachs KS orientation relationship. Do you know what an orientation relationship means? Okay, good. So it's what you get, but we also see sometimes Nishiyama, Wassermann for some minor fractions also being there. And this is very important because we have some interfaces between two different phases which show this orientation relationship, sometimes also with some deviations of the ideal orientations, but still fulfilling. So we have coherent interfaces, at least semi-coherent interfaces, and we have non-orientation relationship interphases. So the same two phases come together, but the interface doesn't fulfill an orientation relationship. That means it's not a semi-coherent interface, it's more like a random high-angle grain boundary, but between two different phases. And this will be important because these two types of interfaces have very different diffusivities. One being very ordered, one would expect diffusivity is low, and one being disordered, giving rise to enhanced diffusion along that interface. So, the following defects are important. Misorientation parameters, like which axis and angle of the misorientation we would have, and also the grain boundary inclination is a very important aspect of this. Especially also the average length of all these grain boundaries as well as the interface boundary and the connectivity. So is it percolating pathway or is it not a percolating pathway is of large importance. Then basically for these complex systems with all these different types of interfaces and different types of diffusion pathways, we need to then solve the diffusion equation and we need to solve them together. This is showing you how you can analyze a microstructure in order to do so. So you basically use EBSD, electron backscatter diffraction, for the phases and then analyze how much low and high angle grain boundaries in each phase separately are present, and then also how much of the interface boundary between two different phases are present. And you can also use that information later on in post-processing to analyze how interconnected are these 2D defects. And it turns out that the interface boundary in this eutectic high entropy system, this dual phase high entropy material, are providing the most abundant 2D defects. So it's the longest area per volume from these interface boundaries as compared to the grain boundaries in these individual phases in this microstructure. And when we now again use diffusion measurements, and this is showing you on a comparison on a 1 over absolute temperature scale, so not homologous temperature scale, we need to first know the volume diffusion coefficients. We want to get the interface diffusion coefficient for the first time, but as you know from our discussions during the previous lectures, we need always to know the volume diffusion coefficient in order to calculate grain boundary or interface boundary diffusion from these solutions of the diffusion equation, because of the fact that we often correlate the dGB to the dV. And since this was not known, we measured this also. And this is just then information necessary to proceed further. We could not use the compositions for the two eutectic phases themselves, because when we produced them in the pure form, they were unstable against precipitation. So we used slightly different compositions which have the same structure, FCC and B2, but which have slightly different compositions so that we avoid precipitation formation during the diffusion measurements. These are then the volume diffusion coefficients. And then following the theoretical work by Mishin, we have to basically relate our interphase and grain boundary diffusion coefficient measurement not to the individual volume diffusion coefficients, but to an effective volume diffusion coefficient, which is calculated as written here. Yeah, then also the segregation factor is an effective value, but our microstructure analysis confirmed that we don't need to worry there because segregation factor will be close to unity. And then you have to do quite a bit of measurements if you want to take the interface diffusivity as a target to measure, because of these multiple interfaces and interface types which you have present in your material. So we did penetration profile measurements for the radio tracer nickel in the eutectic system, targeting the interface diffusion coefficient, and then also in these single phase alloys, both in the FCC and the B2, and then did C-type as well as B-type diffusion measurements. So we measure grain boundary diffusivities directly. We basically assume that we measure the interface boundary diffusion also directly in C-type regimes in the eutectic system. And from the data we gather, we can confirm that this is correct, because interface diffusion is faster than grain boundary diffusion. So it means these C-type kinetic regime conditions to solve diffusion equation are even better fulfilled in this case. But this was not known a priori ahead of time, right? Because nobody has measured interface diffusivity so far. And we then can conclude that interface boundaries are showing much faster mass transport along the boundary plane as compared to grain boundary diffusion. So it means one has to really take this into account if you think of interconnects. Whenever you bring two different materials together, not only for high entropy systems, they might be just a convenient model system. And then we basically have to worry about fast diffusional transport along this boundary plane. We also did time of flight secondary ion mass spectroscopy measurements in order to confirm, because for such a complex microstructure it might really be good to have visual information about where does your tracer go. In this case, again, it's non-radioactive but a stable isotope. And basically you see some of the stable isotopes enriched in these regions where basically the tracer runs along a phase boundary and comes and touches or runs against an interface boundary. So it means this is really some verification that we have interpreted the radio tracer diffusion correctly, because there we cannot have any visual information about how and where the tracer really was going. We can also analyze from this time of flight secondary ion mass spectroscopy measurements the diffusion profile, the penetration profile, to analyze diffusion coefficients. As I said, accuracy will not be so high as compared to the radio tracer method, but still it's good enough. So we can obtain the penetration profile as a function of depth and then do the normal analysis, what we have talked about over the past lectures, and then basically get a confirmation that the diffusivity values which we obtain are rather similar. to what we get from the radio tracer method. When we now look at the Arrhenius dependencies for the grain boundary triple products and also the double products, because segregation factor is roughly unity, as I said, then we basically can compare here the values in the pure FCC phase, so one phase of the eutectic, in the pure BCC, B2 phase, the other phase, which forms the eutectic, and then some measure or some data analysis done for the interphase diffusion in the binary dual phase high entropy system. And there you see several different symbols for eutectic slow and eutectic fast. This is because for some of the diffusional regimes, we had to test different solutions of the diffusion equation, because for the interphase diffusion, it's even more complex in terms of whether you are in B, in C, or in a transitional BC regime, giving you different solutions for the equation. But basically, what you can see is that these diffusivities are showing rather consistent behavior, specifically when we try different solutions of the diffusion equation. And we have really one interphase diffusion component which is fast and one interphase diffusion component which is slow. And that is basically related to the two types of interphases or interface structures, one which is having an orientation relationship, Codium of Sachs, and the other one having no orientation relationship, providing fast diffusion. The interphases without orientation relationship, and the slow ones are the ones which have the Codium of Sachs orientation relationship. So this is again grain and interface boundary diffusion in this eutectic system as compared on homologous temperature scale, because again we compare it with different materials, so we have to take into account that the melting temperatures of these materials are different, and so again the homologous temperature is the right way to compare those. And when we look at it, we have looked at many of these plots over the past 12 days of this lecture series, then one can say that the grain boundary diffusion or also interphase boundary diffusion in these chemically complex alloys can be higher even than diffusion rates in pure matrices or highly ordered alloys with lower configuration entropies. So what we have said today also for these non-FCC high entropy systems in volume diffusion also is true for the grain boundary diffusion, also is true even for interphase boundary diffusion, that there is basically no simple rule. I'm sorry about that, but we cannot say a priori diffusivity in a high entropy system will be higher or slower, lower than in a chemically much more simple material system. This is, I think, again, true if we again show here a comparison based on the configurational entropy of the double or triple product, depending on which alloy we look at. There is a slight general trend of grain boundary diffusion retardation in random alloys with increasing configurational entropy. But, you know, this is one order of magnitude, right? And you would expect it to vary at least by this amount if you can increase the chemical complexity by adding now new different constituents having a different electron configuration, maybe a different tendency to form hybridization and so on. So this, I think, cannot be put completely on just the configuration entropy itself. So for grain and interface boundary diffusion, I think it's important that the specifics of the structure of an interface between two different structures is as important as of an interface called grain boundary. So for some grain boundaries, we know if they have a very highly ordered structure, maybe they are a specific CSL type of boundary, then diffusion will be much slower than in the volume. A typical example is the twin boundary. If it's a fully coherent twin boundary, you cannot measure really diffusion because it's so slow. But if it's a rather disordered structure, so not any type of special orientation relationship, then these grain boundaries seem to feature much more enhanced diffusivity along the boundary plane. And again, there is no tendency in a generic form that would relate configuration entropy, high entropy behavior to how transport along an interface or a grain boundary would work out in the end. So what have we learned about high entropy alloys and compositionally complex alloys? I would say microstructures are rather similar than what you find in normal alloys. I didn't see any paper in the literature which reported anything which we haven't seen before. But that doesn't mean these high entropy alloys are bad or are boring, right? Because we have seen some properties really push the limits, especially concerning higher strength up to higher temperatures, still having good ductility at low temperatures. These combinations are very valuable, and so it's great materials which have been created. It's just that it's related to the specifics of the material, but not that new microstructures or so have been formed. Also, they have been formed by similar ways of making the materials and of characterizing them. Certainly at not too high temperatures, one has always to take into account that the term temperature times entropy gets less and often lower than the enthalpy term. So phase formation and precipitation is bound to happen at some lower temperature, and the specifics of the system govern at which temperature this actually takes place. I think atomic radii differences and lattice distortions coming from the radii differences is the most strongly determining factor for the properties of high entropy systems. I think the configurational entropy term is too small compared to the formation enthalpies of intermetallic phases and also of the general enthalpy of mixing values, that it plays really a decisive role, except in systems where you have near zero enthalpies of mixing or enthalpy of formation. This is why the Cantor alloy works so well, but for all the other systems, it's maybe not a very important contribution concerning phase stability and phase formation. I think diffusion certainly cannot be termed in general as sluggish, so this one core effect I think one should cross out in the literature. So it's down to 3 and not 4 core effects. I'm also doubtful about the so-called cocktail effect. I haven't seen it happening so much. So I would say lattice distortions is the one that I feel is most important. For applications, I would say refractory, compositionally complex alloys, dual phase RHEAs, so refractory high entropy alloys, as well as lightweight compositionally complex alloys are probably the ones that make the market soonest. I think they have the most attractive properties, and maybe they also can provide property combinations that we do not find easily in already known materials. So especially high temperature, high strength, this seems to be important. With this, I would also remind you that there are many high entropy systems out there which are not metallic and which do not have purely structural properties, but also functional properties. I think there's a lot of work going on in high entropy oxides, using them for battery materials, for solid oxide fuel cells, and similar things. Also magnetic properties are highly investigated, catalytic properties, replacing some of the not so abundant rare and pure, noble metals. So this is something I would think are future areas which we will see much more attention in the next few years. So with this, I think I'm at the end of my part of the lecture series.